First of all, thanks for coming this afternoon. I do want to give a little bit of attribution to some of the things I'll be talking about today. Alistair Kroll, I met a couple years ago. He's a part of this organization. He asked me to give a talk in New York last September, and I gave a talk similar to this back then, and he invited me back, so I guess that must have gone okay. While I was getting ready for this talk, a couple things sort of came to mind that I wanted to bring up as a matter of introduction. And one of them is a concept that there's not that many original ideas. And when you think about original ideas, things that actually kind of pop out and are different and really make a difference in the world, most things that you look at that have made a big difference kind of had their evolution someplace else. And what happens is people bring these ideas forward and ideas evolve over time. So having said that, I do want to give Alistair Kroll and George Hawkins, who's a friend of mine who used to be the CEO of DC Water, some benefit of the doubt for some of the things I'll be talking about. So I borrowed some of their things. I've already asked them. It's okay. The second thing is, in terms of how technological progress happens, a couple things I've noticed relatively recently is that the big jumps that happen in technology tend to happen when disparate things get together and they realize they find some things that work. And an example of that is DNA genomics, for example. That's a combination of computer science and biology. Before those two things got together, you couldn't do what they're doing now. And now that's promising to revolutionize the world of medicine and human health. It's pretty exciting. Second one is, frankly, machine learning. Which is a combination of statistics and mathematics and computer science. And again, these things weren't necessarily always working together, but those types of things are what actually pushes things forward as a matter of time. So I'm going to use those as a kind of a theme for today's talk, and that is how technologies from different parts of the human endeavor can actually get together and make a difference. And here today, I'm going to be talking about artificial intelligence in a way that might be different than what they talk about downstairs in the exhibit hall. And underground infrastructure, and by underground infrastructure, I mean water and wastewater pipes, and we'll find out a little bit about that in a second. But let me tell you a little bit of a story. In the late 1890s, let's go back in time, late 1890s, New York City had a problem, and you could see that the population of New York exploded primarily as a result of the Industrial Revolution and the fact that there was a lot of immigration going on in the United States at the same time. So between the end of the Civil War and, say, the early 1900s, the population of New York quadrupled, which is an incredible jump in population. This wasn't just New York. This was happening in other large population centers around the world, places like Rome and Paris and London and so on. And this population jump caused a serious infrastructure problem in New York City. And it was such a big problem that the first urban conference that was ever, international urban conference that was ever convened happened in New York City in 1898. Does anyone have any idea what the conference was about? Okay, well, the conference was about horse manure. Why was horse manure a problem in New York City in the late 1890s? Here's why. Because everything was done by horses back then. Transportation was done by horses. Moving goods and services was done by horses. And what was happening in New York City in the late 1890s, that quadrupling of the population brought a whole lot of horses into a very small area. So they had a problem. And here's an interesting little statistic. Horses in general will put out about 5 quarts of urine every day and 25 pounds of horse manure. Now, I happen to grow up in a farm in Vermont, so I know a lot about horse manure. But if you think about that for a second, it was really a pretty serious problem. And if you think about the numbers of horses that were in New York City at that time, it got up to about 200,000 horses in New York City. So you do the math, 200,000 horses times 25 pounds of horse manure, that's 5 million pounds of horse manure every day in New York City. So they had problems. They had horse manure covering the streets. They had people that would have to go out and actually clean out the horse manure so they could cross the streets. And it became a huge problem. So this group of people got together. This was not just New York. London, Paris, and so on, Philadelphia were all having the same problem. So they convened this group in New York City, and they said, we got to solve this problem. After 3 days, it was supposed to be a 10-day conference. They threw up their hands and they said, we don't know what to do. We don't know how to solve this problem. So you can imagine sort of being in New York City on a hot summer day, 5 million pounds of horse manure on the street, flies everywhere, it's hot and muggy, not a very nice situation, but wait, it gets worse. Horses only lasted about 3 years in New York City. So it turns out that the horses that they brought there to do all the work ended up dying, and they left them on the streets. So now you've got a really, really serious problem that's going on here. You've got an infrastructure problem that's almost unbearable. You've got dead carcasses of horses, piles of horse manure on the street. What are you going to do? So this is one of these examples of, you go to New York now, you don't find piles of horse manure. So obviously the problem has been solved. So the interesting thing was the problem was solved from something outside. These folks that went to New York City to try to solve the problem didn't solve the problem. What ended up happening is a guy named Benz in Germany came up with this thing called the auto carriage. And it was happening about the late 1880s. Well, that's what saved New York City from actually having a really, really serious crisis. I'm sort of surprised there wasn't some really bad human health effects that would have happened from that. But it was the motor carriage that came along with the internal combustion engine. That was really what made the difference that helped solve the problem of the great horse manure crisis of the late 1890s. Now, what the heck does that have to do with AI and infrastructure? Well, I'm going to get to that in a second. Let's turn the clock forward. Now we're looking at San Francisco. We're standing in San Francisco here in 2019, and you probably don't pay much attention to infrastructure in general. I didn't when I was younger. Now I pay a lot of attention to it. But things that make this world a first world country, things like streets, power, communications, automobiles, lights, buildings, all those things are infrastructure. And the issue that we're having now is that our infrastructure is aging. And we're starting to see things that are breaking and causing problems all the time. And today I'm going to focus a little bit on water and wastewater infrastructure. But let me give you a little more background on this. This is an example of how much money we've been spending as a country on our infrastructure as a share of gross domestic product. And you can see that in the late 50s, sort of post-World War II, we were spending about 7% of our gross domestic product. This is local and regional and national, all put together on our infrastructure at post-World War II. But now we're sort of in the 3.5% range. We've dropped our overall investment in infrastructure by about 50%. And this is having an effect. And the effect is pretty obvious, that the less you spend on keeping your infrastructure up, the older it's going to get. So you look at things like highways and streets, hospitals, nursing homes, power plants and power lines, schools and colleges and that sort of thing, and then public transport, airports and ports. You can see from this graph that over time, over the past 15 years, things are getting older. As things get older, they break more. So there's one thing that's missing from this particular picture, and that's water and wastewater infrastructure. I got a couple of theories as to why when people talk about infrastructure and you hear about it from a national standpoint, you don't hear a lot of words about water and wastewater infrastructure. There's two reasons, I think. And I'm going to betray my allegiance to my retail water agency in Southern California. We do a really good job of delivering water to our customers. You can wake up 2 o'clock in the morning, turn your tap on, the water's going to be there. 7/24, you've got water coming to your house. It's very reliable. It's high quality. You can drink it all the time. It's actually better quality than what's coming out of bottles. You may not believe that or not, but the regulations are much tighter for drinking water out of your tap than they are for water bottles. And think about this. For 1 liter of Dasani that you might get at Target, for example, you can get 700 gallons of water coming out of your tap. And you don't have to drive to Target to get it. It's right there, 7/24, all the time. So that's one thing. We do that job really, really well. We also do the sewage job very well. You go to the bathroom, you flush the toilet, things go away, everybody's happy. The only time you really recognize things is when those things aren't happening, like the drought we had here in California over the past few years. All of a sudden, it's become kind of a big deal. The second thing is, and that's why I have this picture up here, is that our water and wastewater infrastructure is pretty much invisible. It's underground. You don't see it unless bad things happen. And this is a case of the Romans. They built their aqueducts. Those are quite visible. So they were very proud about the fact that they could build a civilization. Without these aqueducts, and the sewers, by the way, in Rome, they would not have had the civilization they had. That's one of the things that made it possible to do what they did. So what underpins all the other infrastructure we have is water and wastewater infrastructure. Without that, you frankly don't have a civilization. That's why it's so important. So you may notice that over the past few years, we've had some significant problems in some of our water systems. And Flint, Michigan is one example of that. And I don't have time to tell the story right now. But Flint was actually trying to do the right thing. They were trying to get a lower cost water source for their system. And it turns out that the water source they got had a different chemistry. They didn't recognize the different chemistry. That ate away the inside of the pipes and caused the lead to get in the water. The thing that did wrong was not that, because that was a mistake. Then they lied about it. So and they went to jail, which is a good thing. But the point is that they tried to do something good, and a really, really bad thing happened. And that feeds into the natural conservatism of water and wastewater agencies, because they don't want to change things. Things have been working fine for decades. I don't want to make any changes, because if I do, something may go wrong and I'll get fired. Here's another example, and you probably didn't hear about this one, but I did because San Antonio is one of our customers. But there was a huge sinkhole that opened up in San Antonio a few years back because of a flood in their sewer. The pipe collapsed, and in fact, a lady died in this particular incident. Her car ran through this. It was a deputy sheriff. She ran through the sinkhole and ended up passing away because of that. But it's one of those things that occurs because of decaying infrastructure. My point is, we've got a real problem with our decaying infrastructure. Here's an example of what the water pipes look like in the United States, and this is only a few. This is probably breaking all the PowerPoint rules, and it's hard to read. But nevertheless, you can see that the cities on the East Coast, like Philadelphia and Baltimore, have very, very old infrastructure because they've been there longer. Their water and wastewater systems have been there a long time. So those histograms that show the age of the pipes, and the older ones are to the left, the younger ones are to the right. You can see that Baltimore and Philadelphia are quite old. And in fact, George Hawkins, my friend at DC Water, tells a story about how recently, when they were replacing a pipe in Washington, D.C. in one of their streets, they got down to replace this metal pipe, and written on the pipeline was a man's name, and the gentleman's name was a Civil War general. So that's how old that pipeline was. So there's some very, very old infrastructure back east. And you can see that as the migration in the United States has moved more toward the southwest and the west, that those are kind of newer infrastructures. They're not quite as bad as the ones back east, but nevertheless, they're getting older. Here's a second way of looking at it. And this is an interesting graph because you can see that right kind of post-World War II, the 1950s and 1960s, where the United States was spending a lot of money both building kind of new developments. Suburbia was starting to happen. But since then, we've kind of ignored the replacement and repair of infrastructure. And here we are in 2020, and you can see that the wastewater pipes are older than they've ever been, ever. So we've got the oldest infrastructure for wastewater pipes in the ground right now in the United States, and it's getting older, and it's not getting any better. The problem is it costs a lot of money to fix it. So the American Society of Mechanical Engineers civil engineers does a evaluation every few years, and they gave the wastewater agencies a D because it's a very expensive problem. And it turns out there's about 1 million miles of water pipeline and about 1 million miles of sewer pipeline in the U.S., roughly speaking. And it's about $1 million a mile to replace that pipeline. That's kind of the rough number. If you're in Lincoln, Nebraska, it may be 500,000. If you're in San Francisco, it may be 20 million. But on average, it's about $1 million a mile. So 1 million times 1 million is $1 trillion. And so now you're talking kind of big money. And if you're as old as I am, you might remember Senator Everett Dirksen from the state of Illinois when he said $1 billion here, $1 billion there, you pretty much get into real money. Well, this is $1 trillion. And nowadays, maybe $1 trillion isn't so much anymore, $20 trillion in debt, but nevertheless, it's still a lot of money. The point is that all this infrastructure is not going to get fixed in any time soon. We just don't have the money to do that, nor necessarily the societal will to do it, because again, we're doing a good job delivering our water, taking care of our sewage, and you can't see it. So people wait for it to fail for things to happen. And unfortunately, this crisis is impending. It is our great horse manure crisis of 2019. So what are the consequences of these problems? And one of the consequences is the EPA says there's about 75,000 sewer spills a year, and roughly 1 trillion gallons of sewage gets into the environment every year. So that's a lot of sewage. Now, having said that, a lot of that comes from what are called combined sewers. San Francisco is one of the few cities on the West Coast that actually has a combined sewer. That was the way they did sewers back in the old days, where they'd basically run sewers and storm drains together so that when it wasn't raining, the sewage would just go right to the treatment plant. But when it rained a lot and the treatment plants couldn't handle that rain, that sewage would overflow into rivers and streams. Well, that's not so cool anymore. So the EPA, since 1972, when the Clean Water Act was brought to bear, realized that they had to do something about it, and that's what's been happening. So the actual response to these kinds of things has been regulatory. And in 1972, President Nixon, oddly enough, who started the EPA, pushed through the Clean Water Act. And that was the first major piece of legislation that really worked on sewage in the United States. One of the things that came out of that was this thing called the National Pollution Discharge Elimination System, which is a way for the United States and local EPA agencies. For example, we're in Region 9 here in California. Region 9 runs its own little regulatory agencies, and the State Water Resources Control Board in California are the ones that keep track of what's going on with the sewage in the state. They're the ones that effectively regulate all the agencies that are doing sewage and that sort of thing. And you'll find that for the most part, Sewage agencies are public agencies. You do find some private drinking water agencies, but for the most part, they're public agencies. And one of the reasons is there's strict liability. When a sewage agency has a problem with sewage, they got to pay money. And oddly enough, on the drinking water side, that's not necessarily true. For example, in Milwaukee in 1993, when the cryptosporidium crisis happened, 100 people died, and they ended up getting fined $50,000. So because they were obeying the laws, that was okay. California also, in 2006, came out with what's called the California wastewater discharge requirements. I'm sorry I'm doing all this infrastructure stuff, but this is all as a matter of kind of telling you why what we're talking about today is important. We have the most strict laws here in California of any place in the United States. Every single spill, no matter how large, has to be reported to the state of California. And since 2006, the state's done a pretty good job of reducing their overflows, and we're going to get to why that's true in a few seconds. The second thing that can happen is a thing called consent decrees, and these are legal agreements between agencies that keep on spilling sewage and the EPA effectively. And they say, look, you guys have been bad boys. You've got to behave yourself. You've got to make sure you do things better. And they come up with a legal agreement. A lot of lawyers get involved, and these consent decrees happen. Well, $85 billion in consent decrees is quite a bit. What's the problem with that? The problem with that is there's financial consequences. Again, this affects probably the Northeast more than it does out here in California. So when I was talking in New York City, this thing made a lot of sense. But there's some cities back on the East Coast that are kind of Rust Belt cities where the populations are decreasing, and they've got combined sewers, and the EPA comes in and says you've got to separate those combined sewers into a sanitary sewer, which is a separate sewer, and a stormwater. And the problem with that is it's millions and millions and billions of dollars. In fact, I've got a friend, Jeff Wenberg, at the city of Rutland, Vermont. They've got 18,000 residents, and he estimates that the cost to separate his sewer is $125 million. Now, you can imagine a $125 million bill on 18,000 residents, of which probably only half of which are taxpayers. That's a big bill. So the point is, it's a lot of money to try to fix these problems. Is there a better way? And that's the question we're going to answer today. The classical solution, like I told you, is to put pipeline in the ground, concrete in the ground, and it's about $1 million a mile typical cost. So how do we solve this problem? We've got stinking, rotting piles of horse manure, equivalently our pipes underground that are rotting, and how do we solve this problem? So in 2005, my friend and I actually started a solution to this, and I'm going to talk about IoT in a sewer environment. So this is a very specific thing, Internet of Things. Back then it wasn't called the Internet of Things, but when we went to our customers and we asked them what they wanted to do to fix their problem, they told us, just fix the problem, don't tell us how. So we provide sensors that actually mount underneath manhole covers. They've got to be small because they've got to be compact. They've got to be rugged. A sewer environment is about as bad as it gets. They've got to be smart in the sense that they need to be able to sense their own environment and do their own sort of self-diagnostics. Stupid sensors don't make any sense anymore. You want to really put a little bit of intelligence in each one of these sensors so they can kind of tell what's going on in real time. And they have to be low power because you can't run power to these places like manholes all over the place. Communication should be wireless. It needs to be reliable. Obviously, you need to be there all the time. It needs to be ubiquitous. It needs to be everywhere. And it needs to be secure. The analysis provided on this data needs to be real-time, predictive, and integrated. And by real-time, I mean that when things are happening in real time, this information is being analyzed in real time. Predictive in the sense that we can predict what's going to happen in the future. And obviously integrated by bringing different types of data sets together and doing data fusion. And ultimately, what our customers care about is the decision. How do you tell me what to do with my pipeline? Now that I know what's going on underground, what do I do about it? So these decisions have to be trustworthy, they have to be simple and easy for them to understand, and they have to be measurable in terms of doing an ROI for our customers. So this is how the company started back in 2005. Literally, it started in David's den, and David is my business partner. He's a Caltech electrical engineer that was at JPL for a while. And we sat around in 2005, being a couple of water guys that were elected to this water board, and said, we're technologists, we'd like to help solve your problem. We called up our friends in the industry, and they said, gee, what can you do about sewer spills? And that's how the whole thing got started. So we literally started in his den, and we've grown from there. But this is what the actual infrastructure looks like now, sort of more in cartoon form. The sensor is there in the manhole cover reading water levels continuously. We talk to the Iridium satellite network. Why do we do that? We don't send a lot of bandwidth back and forth. We're smart in terms of our data, so we only send what we need to send up to the Iridium satellite system. The cool part about Iridium is it's there all the time. If you think about where sewers are, they tend to be in the lowest topology. So to try to do cell phones, it means you have to look at low angles to the horizon. You don't do well in canyons, and that's where sewers are a lot of time. Iridium straight up, so it does very well. Iridium has redundant ground stations, and they talk to our cloud in San Diego, where we integrate other real-time data like weather data together with that, and we provide all that information to our customers in real time. So this was done back in 2005, right? Which is kind of interesting because if you think about where technology was in 2005, tell me what year the iPhone came out. 2007, correct. This is right about the time the iPhone came out, which seems like forever ago, right? It's really only 12 years, guys. It's not that long. So look how much we've done in that time in terms of smartphones. The technology really wasn't available before then. So if Dave and I came up with this idea in 1998, we would have had a rough time. So the confluence of technology just happened to be there at the right time. Power, communications, computing power, and the ability to put all this stuff in very small electronics worked. So now we're deploying these things in places like San Antonio. This is an example. This is the largest system of its type in the world. There's over 500 of these systems in San Antonio right now that are giving them real-time data that are helping them manage their sewer system so they can avoid those spills and not have to spend $1 million a mile for their pipeline. They eventually are going to have to do that, right? But now at least they got a handle on what's going on. Prior to this, no one knew what was going on in their sewer collection systems. It was unknown. They'd send people out in trucks, open up the manholes, take a look, and that was their data collection system. They don't do that anymore. So what does this have to do with AI? Well, it turns out that water levels in sewers are actually quite revealing. If anyone's as old as I am, you might have had an EKG or gone on one of these treadmills, and they put all the sensors on you. They take a look at what your heart's doing. Well, this is what an EKG looks like, and if you have an EKG problem, they'll send you to a cardiologist. Turns out that sewers have a heartbeat as well, oddly enough. There's two bumps that happen during the day, one in the late morning, one in the early evening, that have to do with residential use, and that it produces a heartbeat that happens every single day. And if that heartbeat starts to change, it means there's something going on around you, just like your arteries are getting clogged with too much fat. You're going to see an anomaly in your EKG. You're going to see the same thing in your sewer patterns. So we've taken advantage of this information, finding out what's happening with our sewers. That's kind of what a normal heartbeat looks like. It kind of goes up and down. It has the same maxima and minima. It has the same repeating pattern. What happens when you have grit buildup, when, for example, a storm comes and dirt and stuff goes into your sewers, you'll end up having grit that builds up. It turns out, if you look at that chart, it's only going up about ½ an inch. There's no way that somebody in a truck looking down a manhole can tell that that's happening manually. So that the ability to instrument these sewers, and you know, this sounds like it's really kind of a simple thing for all the people that are here in the IT world. It really is not for the water industry, because you got to remember the water industry does not change quickly. They do stuff that's been happening for decades. They don't want to change. So this kind of stuff is like rocket science to them. So it's really kind of neat. A blockage upstream looks like this, where all of a sudden, the pipe upstream starts to get blocked, and that's what the pattern looks like. This is what a blockage downstream looks like, where all of a sudden the water starts pooling up. So these patterns can tell you there's something going on around me in my sensor. It doesn't mean you need a sensor in every manhole. You just need a sensor in maybe every 10 or 20 manholes, and you can tell what's going on in your whole system by putting these monitors out there. That's what makes it cost effective. So now I'm going to get into some case studies. And these are just 4 little stories. We've actually got probably dozens of these that we could tell, but I don't have time to go through them all today. I'll buy someone a beer if you can tell me what that is, the picture of. Yeah, it's a tough one. That's Marilyn Monroe's childhood house. She grew up in Hawthorne. It turns out there's one of our units right outside of her house, so we got to take a picture of her house one time. Okay, thank you. And it turns out the Beach Boys came out of Hawthorne too. So if you've ever flown to LAX, and you're on the left-hand side of the airplane, you're at the window, just before you're about to land at LAX, look down, that's Hawthorne. It's right there. It's not a big city. It's 6 square miles. Elon Musk has a thing called SpaceX there now. That's where they run SpaceX. Northrop was there a long time ago. They had a problem. They only had 2 full-time field staff. They got 90 miles of pipeline. They were having 10 sewer spills a year before our system became available, before the technology was there. Since then, they've had 1 spill, which is now 13 years, so this number is actually wrong. They've had a 99% reduction in sewer overflows by using this technology. It's a huge difference. It's not just 10 or 20%. So what they did is they went back and found out where all their problems were and said, I want to see what's going on there all the time. And by the information, they were able to reduce their sewer spills. Tremendous amount. Their estimated net program savings at this point is $2.5 million. Interesting story. This kind of tells you how cities work sometime. Their finance director changed out, and they got a new finance director come in, and they came in one day and they said, so what's this line item on our budget that says SmartCover monitoring systems, and their The supervisor said, well, that's to stop sewer spills. And she said, well, we don't have sewer spills. Okay, that's why you don't have sewer spills. San Antonio Water System. This is SAWS. It's the sewer and water agency for the city of San Antonio, which I think is now the 6th largest city in the United States. We did a cleaning project with them where we said, look at, they were doing sewer cleaning to keep the sewer spills from happening. We'll tell you when you need to clean your sewers because we can tell what's going on in your sewers by using our EKGs. We were able to do a 94% reduction in their cleaning. At the same time, they had no spills. So now we've got more than 200 of those installed in San Antonio. Their net program savings is $3.1 million. So now these technologies are, again, producing orders of magnitude changes in how they do operations and saving millions of dollars at the same time. It's a great application. Again, this is not rocket science. This isn't bleeding edge stuff, but it is the application of the type of AI that we can to these utilities. Escondido, California, which is my hometown. Maybe you remember the big rains in the early parts of 2017. We had what's called an atmospheric river hit Southern California. It just came in from Hawaii. They called it the Pineapple Express. We've got 4 inches of rain in a couple of days, which for us is a lot. What happened was a pipe collapsed again. It's kind of like that pipe that happened in San Antonio, but it happened this time that there was a sensor 5 manholes upstream. At 2 o'clock in the morning, we caught that pipe collapsing. The folks in Escondido got the alarm. They sent their folks out to fix it, and there was no spill. So this is a great example of what would have happened. We talked to the utilities director, Chris McKinney, a little bit afterwards, and he said, you really saved us $5 or $6 million. That was going to flood into an industrial park at 2 o'clock in the morning because there was nobody there to know what was going on. So you can imagine all the lawsuits that would have happened based on that. So again, a big savings. Another example, if you've ever been skiing in Colorado, Mount Crested Butte, Colorado is a small little ski town there. They've got 6,500 residents. They had sewer spills in 2005 and 2006 that caused the state to come in and said, if you don't fix this problem, we're going to pull your operating permit. If you pull an operating permit for a sewage plant in a ski town, you basically shut the ski town down. There's nowhere to go from that point. So they were kind of at a really rough spot. Their engineer decided that it was going to be about a $10 million upgrade to fix their problem. They found us serendipitously by being in San Diego, and they saw an article about us in the paper. They went back to the state of Colorado and said, hey, if we can install this system and stop sewer spills, is that okay? And the state correctly said, we don't care how you fix the problem, just fix the problem. So I met Frank Lick, who was their general manager at Chili's in Colorado Springs. He hands me a check for $96,000 and said, fix the problem. So we did. We put these in. There's been no spill since deployment, and instead of spending $10 million for their pipeline, they only spent $100,000. Their consent order was lifted, and it was 100-to-1 immediate ROI. So again, orders of magnitude. When you apply intelligent technology, intelligent digital technology to a tough problem, an older problem, you can really make a big difference. This is kind of where we're going. I'm getting to the end of the talk. This is sort of how the whole world of sewers works. Inputs to sewers are things like streams and rivers, tides, rain and snow melt, groundwater levels, and soil moisture. Black water is what comes out of your house. We call that black water in the industry. All those can be monitored for the most part. If they're all monitored, you know what's going on. The next level down is the transport and process part, where you can have uncontrolled runoff. People have used green infrastructure to help absorb stormwater. That's been very helpful from the sewer standpoint. Gray infrastructure is the standard stuff, pipes that are in the ground that people are fixing. All of that goes to really one of 4 places, the wastewater treatment plant, WWTP. It overflows its sewer or a stormwater outflow, and eventually it all ends up in the environment. Now, I will say that with one caveat, and you're probably recognizing there's things going on in California now that are changing that. In fact, the state is talking about completely restricting stormwater from going into the ocean and capturing 100% of that. If we did that, we wouldn't have any water problems anymore. So I'm going to put that in there as the next thing that's going to be happening in the future, and that's potable reuse. And I won't talk about whether it's direct or indirect potable reuse, but nevertheless, it's an important part. So this is kind of the whole picture of how sewers work. And all those M's, by the way, are places where you can put monitors to see what's going on. That's the IoT and AI part of this infrastructure that we're working on. Another thing we're doing is I'm going to be going back to Washington in 2 weeks to try to make a difference in some of the legislation that's coming out. They are saying there will be an infrastructure bill this year. And again, when I say infrastructure, people talk about airports and highways and stuff like that. And a lot of times they forget about water. So I'd like to ask you as citizens, talk to your congressman or woman and talk to your senator and tell them, pay attention to water, because that's really what really matters, especially here in California. We recognize that. But the point is that if we're going to spend trillions of dollars on infrastructure improvements, it should be done smartly. You should know where the problems are and prioritize them properly. And you're not going to know that unless you can look underground and see what's happening with these types of systems. So, in conclusion, the problem we've had is sewer overflows into the environment that are bad for the environment, bad for human health, and obviously they're very expensive to fix. We talked about the problem. This is our great horse manure problem of 2019. In this case, it's not horse manure, it's another kind of manure that's getting in the environment. And the cool thing is people like you are helping to provide the solutions with low cost, high speed, smart electronics, good communication, and data analytics that happens in real time. All that stuff can help solve the problems. And the results have been phenomenal. And just some of these case studies I've shown you demonstrate that. Lots of money can be saved, rates can be kept under control, and most importantly, the environment and human health can be fixed. Thank you for listening. Any questions or comments? Sir. So the question is, how do you see it working for any kind of other subsurface infrastructure like oil? I think there's plenty of places for that happening, and if you live anywhere near San Mateo, you've probably had experience with that kind of thing. That's not our particular area of expertise, but certainly the whole issue of aging infrastructure underground, I'm sure there's ways that it could be very helpful. Sir.
So you started out your talk and you said there were very few new ideas, right?
Yeah.
Over the long term, I mean, you looked at this for a long time. $1 million a mile, like from a capital expenditure, is crazy. But what do you know? Is there anyone else out there that's trying something like a moonshot idea to like fix this at scale?
It's interesting you use the word moonshot, because George Hawkins, who I referred to earlier, who is now actually retired from DC Water, has an organization called Moonshot, and his moonshot is to try to inculcate technology into the infrastructure world to try to help solve the problem. Over time, just like in Mount Crested Butte, they're going to have to replace those pipelines. But the point is they can extend the lifetime of those pipelines if they can do the proper monitoring and make sure they can fix those problems. In San Antonio, when we first went down there, the first thing we were doing is they were under consent decree. So they've got a several billion-dollar consent decree they have to deal with. They've got a whole bunch of pipelines that are just dying and falling apart. They put our systems there first to keep an eye on those so that nothing bad happened. So you're kind of balancing the whole benefit of no spills at the same time you're kind of pushing out in your capital expenditure. It's going to have to happen, but if you can do it as a planned thing as opposed to an unplanned thing, obviously you're going to save money over the long term, and rates will be kept a little bit more under control. Good question. Anybody else? All right, thanks a lot. Appreciate it.